Good morning, everyone. Happy Friday. How y'all doing?
All right.
Any questions at this time before we get started? All right, please let me know if and when you do have any questions. Just a sec to find my mental starting position. All right, so we've been talking about Newton's laws and discussing various types of force and how they interact with Newton's laws. And we started today with a little bit of practice to review what we did last time. We're going to place a 10 kilogram box on a table, and some various forces are going to begin acting on it. We've got a 200 Newton force west or left, and a 250 Newton force east or right. And I'd like you guys to draw for me a free body diagram, which is the fancy term for a picture that shows arrows for all of the forces currently acting on this particular box.
Is the 250 pushing east or from the east?
Pushing towards the east. Usually I will tell you what direction vectors point to rather than where they are coming from. Just to check in with how you guys are doing. How many forces can you identify acting on this particular box?
Three.
Three's a good guess. I see at least one person with 4 fingers up. And 4 is actually the number of forces we are looking for here. Question tells us 2 of them. 250 newtons east and 200 newtons west. Using your knowledge of physics and the universe, what other forces might be present acting on this thing if it's
Gravity.
Yes, if it's on Earth and on level ground. We got gravity down. And what else? Normal force.
Normal force, yeah.
As long as you are on a surface, it's going to exert force back out as long as you are pushing into it. Gravity is going to pull us into the surface, so the surface will push back, and the interaction between these two things is why the box does not fall through the earth. So there are 4 forces here as a part of our diagram. And now I will put it to you, given these 4 forces present, what is the net force currently acting on this box? At least one person motioning that it will point to the right. The net force will point to the right. What will the value of net force be? 50 newtons. Very good. As long as you are not accelerating up or down, that implies that the 2 vertical forces should be equal and opposite. So whatever number these 2 things have, they will cancel out. That just leaves 200 to the left and 50 to the right. Those oppose each other, so when they add up, you're really subtracting one from the other. It's technically 250 plus negative 200, and that's where the 50 Newton net force comes from. So, net force, 50 newtons to the right. Now, given what we discussed on Wednesday, what should the value of gravity and net force be in this specific situation? We already know the value of the 2 applied forces, but what would the value of gravity and net force be on this box? Say it again. I feel like I heard someone mutter it. I think you're right, I just wanted to check. My ears aren't great.
98.
98. Very good. Just to confirm where that number comes from, gravity is equal to mass in kilograms times 9.8. So if it's a 10 kilogram box, 10 times negative 9.8 is going to give us gravity of negative 98 newtons down. And if the ground is successfully giving us enough normal force to keep the box from falling through it, it should be 98 newtons up. So we have now identified and numbered every force present here. Well done. Last question. If the box's mass is 10 kilograms, what should its resulting acceleration be as all these forces add up together? Bless you. 5. Very good. Newton's second law tells us the relationship between net force, mass, and acceleration. If net force is going to be 50 newtons to the right, 50 equals 10 times A. The resulting acceleration will be 50 over 10, which is 5 meters per second squared to the right. So if the net force points to the right, the net acceleration will also point to the right. Net force and acceleration always point in the same direction according to this formula, because they're the only 2 vectors present in the formula. When something is falling straight down, it's because net force points straight down. Or rather, when it's accelerating straight down, it can technically move sideways and accelerate down at the same time. How you guys feel? Thumbs up? At least one thumbs up? Any questions or issues with any of this material in reference to Wednesday. All right. So, like on Wednesday, we're talking about different types of force and how they all interact with each other. Today we're going to begin looking at two more of those types, namely because they will start popping up in lab next week. Next week's lab will involve pulleys and ropes and eventually friction. Main one on this slide that I want to begin paying attention to now is tension. We'll come back to friction once tension makes sense. The definition of tension is a force exerted. It doesn't technically need to be by a string, but it is very commonly exerted by strings and ropes and cables and things to that effect. The main qualifier for tension is it has to be an inward pointing force that is a result of an object being pulled outward on both sides. Oh, perfect. Yeah, this was here. I'm going to demonstrate using this spring. Now, if I just allow the spring to sit in my hand like this, I'm not pulling on either side of it, then this object is not currently under tension yet. There are forces acting on it, gravity down and normal force from my hand pointing upwards, but those forces do not pull on it. They're not pulling outward on its two ends, so it's not under tension yet. When I take hold of it by the rings on either side and pull out, I have now placed the spring under tension. I am pulling outwards on either side of it. And what Newton's third law tells us is, as a counter to me pulling outwards on both sides, the spring is in turn going to pull inwards on both sides. And that is the definition of tension. The actual tensile force is the spring pulling inwards on both of my hands. So the definition of tension is the force that the spring is exerting right now inwards on both sides of itself. And so anytime you utilize a rope or a string or even I forgot English for a second there, spring, the force it exerts when you pull outwards on it is called tension. So it's just a specific name for the force that the rope or whatever have you is applying on whatever it is attached to. The thing about tension is it has a couple of quirks. One, you can only have tension when you're pulling outwards on something. If I pressed inwards on this spring, then it's not technically exerting tension anymore. Instead of putting it under tension, I would be compressing it. And ropes don't tend to do very well under compression, as you might be able to see here. Ropes are kind of designed to be under tension instead, and as a result, so are most springs. I can demonstrate with a more rope-like object as well, using my charging cord. This object does okay under tension if I pull outwards on both sides, but if I push inwards, it kind of stops working as intended. So tension is again defined as when you pull outwards on something, it's going to pull inwards as a response. And what's interesting is the one object, I keep misplacing my erasers. This black box here is going to represent a piece of string. And in order to put a string under tension, some force has to be pulling outwards on both sides. So these orange arrows are going to represent that outward applied force. I'm just going to give it an arbitrary number of 10 newtons on either side. And neither of those orange arrows is something that the rope itself is doing. Those are both things that are being done to the rope, outward from either side. So those are both outside of the rope itself. Tension is defined as what the rope is doing in this scenario. And according to Newton's third law, what the rope is going to do is pull inwards on both sides. So the green arrows here represent tension, commonly abbreviated to uppercase T, but you could also call it force subscript T. It's still a force, it's still measured in newtons. And the green arrows here are both simultaneously the rope's tension response. So the quirk with tension is if a rope is exerting tension, it is exerting the same amount of tension inwards on both of its ends, both of them simultaneously. So all ropes under tension, all ropes exerting tension, are exerting the same force inward on both sides as a counter to some force being exerted separately onto the rope outward on both of its sides. You may not have ever heard it described this way, but you've still observed the force acting on both sides before. And rather than draw a picture sideways, I'm now going to draw a vertical picture to try to give you some context for where you might see this sort of thing. Let's say if instead of oriented sideways, you've got a rope hanging vertically. Let's say this is an action movie and someone is swinging from this rope. And what the rope is going to do to help this person actually swing is the rope is going to be pulling upwards on them, right? It's the whole purpose of the rope. If the rope was not pulling upwards, this person would just fall, right? So the rope is going to pull upwards on this side. But in the action movie, sometimes there's a very tense moment where you can see that the rope might break loose from the ceiling, right? Or perhaps a chandelier will break loose or something like that. There's always a moment in these types of movies where something connected to the ceiling might break loose. And what's happening there is, because the rope is pulling upwards on action star here, that means it has to pull downwards on whatever the other end is connected to. And that downward force is now pulling on the ceiling, possibly breaking the ceiling, and thus creating the tense moment where it's not that the rope is necessarily, the rope might snap. That happens in the movies too. But the way that I've drawn this, the rope is physically going to be pulling down on the ceiling, but like it's pulling up on the person swinging from it. And that means the rope is exerting a force on the ceiling, and that is why sometimes in both reality and in the movies, the rope physically breaks the point where it's attached to. Like if I tried to attach a rope to these ceiling tiles and swing from it, the rope is going to pull down on the ceiling tile and this tile is going to snap because they weren't meant to support the weight of a human being. So all ropes, all objects exerting tension pull inwards on both sides. And I bet you've noticed that subconsciously. How's this feel so far? Okay. Questions thus far? Okay. And I'll add again, the rope is doing this because it is being pulled outward on both sides. The main character's force of gravity is going to be pulling outward on this end. Meanwhile, if it's connected to the ceiling will be pulling upward on the other end. So, in both pictures, the orange arrows are outward pointing forces that other things are exerting on the rope, and the green arrows represent the tension force that the rope is exerting inwards on both sides as a response to that. So the definition of tension is always inward on both sides, and always the same number on both sides, that the rope is exerting as a response to being pulled outward on both sides. Questions for right now? Okay, we're going to come back to friction. I'm going to define friction later. I want to kind of show you one of the types of questions that will involve tension. And the example is going to be that of a hanging object, but instead of a person mid-swing, it's just going to be a box hanging in place, for simplicity's sake. Excuse me. In this scenario, we have a 100 kilogram box, sat right there. It is connected to a series of ropes. Now you might see a series of ropes like this, say in a dock situation where a lot of ropes are being used to lift cargo up out of things and transport them like out of boats and onto the pier or vice versa. You may also see it in theater because there's always ropes holding things above the actors, like sandbags and props and part of the set and things like that. So there are very complex rope and pulley systems that exist like this, and the reason that the math we're about to do is important is because certain ropes can usually only hold about so much tension. If you get into engineering or any of the fields that I've mentioned, all ropes, all materials are only able to handle a certain amount of tension, kind of like how your own body can only bear so much force or your bones snap. If a rope is holding more tension than it is able to bear, it's just going to snap, and then things start falling, and that's bad for everyone. So what engineers will commonly do is they will draw out the scenarios, use the math to try to figure out what tension each present rope is going to be under, and double check to make sure that all the ropes present can bear that much tension. So what we're going to do now is figure out how much tension each of these three ropes is under in order to hold this box in place. This is the basic setup of what we're about to do. Sound clear? I'm going to calculate what the tension in each of these ropes should be. All right. I'm going to roll the board up so I can draw directly on top of my picture. There are a total of 3 ropes in this scenario that are all working together to hold aloft this 100 kilogram box. And those 3 ropes are all going to exert different tensions. So let's label the ropes first. I'm going to call this bottom rope here rope 1. Well, you know what? I'm going to call this one rope 1 because they labeled the relevant angle as A1. I'll call this one rope 2 because its relevant angle is labeled A2. And so this bottom one will be rope number 3. Any questions with that numbering system? Okay. Each of these ropes is going to exert a different amount of tension. So that means we're going to be looking for Gesundheit, tension 1, 2, and 3. And each of these tensions through each ropes are going to be pulling in different directions on each side of said ropes. I'm going to start at the bottom point here and kind of work our way up to draw arrows representing the direction each tension is pulling. This third rope here, the bottommost one that is directly supporting the box, it's going to pull upwards on the bottom end, and that's what's holding the box up, and it's going to pull down on its top end, because it always pulls inward on both ends. So it's consistently inward, but exactly what direction that means will change from one end to the other. This is why the rope is able to hold up this box but it's pulling down on the other two ropes. That's why it needs support from the other two ropes. It's pulling down on this point, and it's relying on the other ropes to pull up at that point. So likewise, rope number 2 is going to pull up and to the left at that side, which will cause it to pull down and to the right where it connects to the ceiling. And rope 1 is going to pull up and to the right at this point, and therefore down and to the left where it connects to the ceiling. So 3 different tensions, each pulling in slightly different directions depending on which end of the rope you're examining. And we got to figure out what all 3 of these tensions are equal to. Where do you guys think we should start?
Tension 3.
Tension 3. It's a good thought. That is because this 3rd rope down here is entirely supporting the weight of the box. So tension 3 has to be more than enough, has to be equal to the weight of the box in order to hold it here. So the first thing I'm going to recommend us do, whenever you're doing tension problems like this, it helps to kind of divide it up into multiple points, examining how the tensions interact at multiple points on the diagram. The first point I'm going to recommend we examine is right here, where rope 3 connects to the box. We're going to examine all the forces present at that spot and figure out how they all work together. So at that spot, we're going to try to identify all the forces present that are affecting that spot right there where the rope connects to the box. The forces that are going to act there are tension 3 upward, and what other forces must be present?
Gravity.
Gravity, specifically the weight of that box. So, tension is interacting with the force of gravity. I'm going to further label that force gravity box, just for clarity's sake. These 2 forces are interacting at that position. Net force says they are going to add up together, and for this whole system to work correctly, if the goal of this whole system is to simply hold that box in place, what must the net force at that spot be in order for the system to be working correctly and the box to be held in place?
Greater than the mass of the box.
You might be jumping ahead a little bit. You're correct in that the tension must be able to support the box. But what I'm asking is, for this box to remain in place, what must the net force acting on it be equal to?
Doesn't it have to be equal to the same, like the same tension as like T1 and T2? Is it giving on the box?
You guys are kind of skipping ahead. You're answering different questions. You're making good observations. What I'm asking right now is, at this spot right here, where rope 3 is connecting to the box, what is the net force on this point if the goal is to keep the box stationary? 0. If you want to keep things in place, net force always has to equal 0. Net force is defined as the sum of all the forces present at that spot, and in order for that box to remain in place, they must be adding up to 0. And this is where we get the math that points out, eventually, tension 3 must be equal and opposite to the box's weight at that spot. So again, you're all making correct points. You're just kind of skipping ahead and answering questions that I wasn't asking yet. But you're on the right track. I'm proud of you guys. So, tension 3, start plugging things in, is going to be equal to the weight of the box. That's going to be equal to the box's mass times negative 9.8. and they must be adding up to 0. Therefore, the value of tension 3 must be 980 newtons. That means if you're using a brand of rope that cannot support a tension of 980 newtons, things will break and you will, at minimum, probably lose your job if you were the one designing this system. Again, if you were the person building this, you'd want to make sure that the type of rope or cable that you were using can support way more than this amount of tension. If you get into material sciences, every different material of every single, pardon me, that's a sign I need water. If you get into material sciences, materials engineering, you're going to be looking at a lot of different tables that will list the various different properties of specific materials like tensile strength and things like that. So if you were building this, you'd look up the tensile strength of all the ropes you can buy, and you'd make sure that the strength of the rope is bigger than this number. Questions so far? All right, so that's one of the 3 tensions already solved. That would be the tension that this bottommost rope is under. And that's all the forces currently acting at this spot, so that's all the information we're going to get from this spot. So now we need to draw our attention to a different point on this whole system. And the point I'm going to draw your attention to is this one right here, where all the 3 ropes connect. At that spot, since they're all connecting, we can use the information we've already found to help us figure out what the other 2 tensions must be. So let's describe all of the forces acting there. In that position, we've got all 3 tensions acting, so T1 plus T2 plus T3. They are all tied together at this point, all pulling away from this spot, so they are all acting here. And once again, if the point of this system is to keep everything locked in place, what must the net force be? What must all these tensions add up to? 0, very good. So all these forces must again be adding up to 0. Now, all these ropes point in different directions. That means it's trick time. No, you're entitled to your opinion. I'm going to modify the picture slightly. So T2x, T2y. T1x, T1y. The problem with T1 and T2 in this picture is they are not pointing in single axes. They are one or the other. They're on angles, both of them. And as a result, the tensions of each of those ropes are functionally the hypotenuses of 2 right triangles. Yes?
Why are they not going to the corners of M and A2?
They can. They probably should. Sometimes I just stop drawing early because I know things that you guys don't. But you're correct. In the interest of thoroughness, I do want you guys to call me out when I do something that doesn't make sense. Because T1 and T2 are pointed at odd angles, they have to be divided up into their components, and then rather than one net force equation, we're actually going to have to break this up into its component axes as well. So I'm going to rewrite that equation. Net force X, we're we're gonna add up all the X forces that are acting on this second spot. So that's gonna be T1X plus T2X must add up to 0. Interestingly, T3 does not have an X component, so it's actually not present in this specific equation. And then separately, net force Y would be all the Y components added together. And T3 is in the Y-axis, so it will be present in this version. And so, in order to proceed, we're going to have to use a little bit of trig to divide our hypothetical T1 and T2 up into their components, and then look at our two axes separately to see how they all interact with each other. Questions so far? Yes.
Why is it T3 in the FX one?
So, if we examine this spot right here, what direction is T3 pulling in? Straight down. And if it's straight down, what would its X component be? 0. So, technically speaking, we could say that, like, I could write out this plus T3X equals 0, but this will be 0.
Okay.
Like if we were to write this out in terms of its components, they'd be 0, 980. Again, this is one of those things that I do because I know that in advance, but you're correct in pointing that out. Its X component is just 0, so I kind of cut it out the first to begin with. But for thoroughness sake, I will go ahead and add them. And I'll just list over here. T3 equals 0, 980. Furthermore, I'm getting at myself. So its X component is 0, it's not going to contribute to the X axis. That's why I wrote it that way the first time. Answer the question. Okay. So, we've already got T3 in terms of its components. Now we have to do the same thing with T1 and T2. Now we don't know a value for T1 or T2 yet. The whole point of this is to find one. So this trig is actually going to be looking, we need to set up our trig equations, but they're going to kind of stay equations. We're not really going to get a numerical answer out of them yet. Looking at T1 here, we've been told that angle 1 is 30 degrees. And that means that this one will also be 30 degrees. Does that picture make sense? Okay. From this angle's perspective, which leg, Tx or Ty, is going to be opposite? Very good. And that leaves X as the adjacent. So Katoa, sine of our 30-degree angle is going to be T1y over T1. And likewise, cosine 30 is going to be T1x over T1. This tells us T1x will eventually be equal to the value of T1 times cosine of 30, and T1y will be equal to T1 times the sine of 30. Once we have a number for T1, we can pop it in there, we'll figure out the components. Yeah, we're kind of going to use the components to find the tension number. So we're working a little bit backwards. We can do the same thing over here to T2, except it's 45 degrees instead of 30. The equations would look pretty much the same, but I'll write them out. Sine of 45 is T2y over T2. Cosine of 45 is T2x over T2. Therefore, T2x would be T2 times cosine of 45. And T2y is T2 times the sine of 45.
We gotta do this like by ourselves in the test.
Yes. That's why we're practicing it now. And I might only, look, the test is gonna have multiple questions on it, and it's, sorry, I'm mixing my points together. When I write my tests, I'm keeping in mind the fact that you guys are students, and it's supposed to take you guys an hour. You have longer than an hour, but I write it as if it was to take an hour. And for that reason, I don't try to make the questions all super long. I like doing the longer ones in class so you get the practice in.
It's
But
crazy.
on the versions you're expected to do with a time clock in a test environment, I write the questions so that each question is not meant to take forever. It's meant for you to look at it and gauge what you know. So keep that in mind when I write the test questions specifically.
Oh, man.
I'd rather do the hard stuff with you in here than make you miserable during test time.
So this like the hardest question we're gonna do.
It would be the most trig intensive question. Yeah, if I gave you this on the test, it would be the long one worth the most points. I said if, doesn't mean I would. There's other things I can make into the hard question. Now, other questions, concerns? Concerns mostly? Anyone concerned? Okay. So, now that we've got the components written down in terms of T1 and T2, I'm going to take the components and plug them into our two equations here. T1x is, I'm running out of ink. Bless you. T1 cosine 30 plus T2x, which is T2 cosine 45, and T3x is 0, must all add up to 0. That said, what direction, positive or negative, does the x leg of T2 point?
Huh?
Looking at this picture, notice that the two x legs work against each other. So that means we have to make one of them negative.
Doesn't matter which one?
Doesn't technically matter which one, because ultimately, to solve this one, we're gonna have to send one of them to the other side anyway, and the negative would just cancel out. But one of them has to be made negative because they oppose each other.
Yeah, that's not.
Okay. Yeah, you can define T2x as the positive one if you wanted to, as long as one of them is negative, setting this up. And to define this one as well, it would have T1 sine of 30 plus T2 sine of 45, and in the y-axis, T3 is present, so this is where the 980 we found earlier would live. They all have to add up to 0. Of these three components, which one should we make negative?
The 980.
Yes, the 980. Because from this point's perspective, the direction of T3 has flipped, because all ropes pull inwards on both sides, and that means from one side of the rope to the other, the direction switches. T3 pulls up down here, but it pulls down here, notably opposing the Y legs of our two other ropes. So for that reason, whatever sign you put on the first two, T3 needs to have the opposite one. Because it is opposing the other two at that specific spot. And the perspective and frame of reference is important and will continue to be important. And that's the setup. Now, we're almost out of time for today. I don't want to hold you up before the weekend. You may have noticed at this particular point that neither equation is completely solvable by itself. We've hit a 2 equations, 2 unknowns scenario. So the reason I wanted to do this one is to practice that with you. But we're out of time today. I'm not going to hold you up before the weekend. So we will resume this one on Monday before talking about friction. Do hold on to your notes. You make sure these 2 things are in your notes for when we resume. Do we have any questions before breaking for the weekend? Okay. If you don't need anything, be working on your homework and do ask me questions about your homework. And I'm rambling. Do have a nice weekend.